What if the blueprints for the modern world were already drawn 600 years before the modern world arrived? And what if the engineers who drew them had no engines, no factories, no physics textbooks, and no word yet for the discipline they were inventing? We begin not with a monument, a factory, or a patent office, but with a book that should not contain what it contains, a book whose pages describe machines that would not be built, fielded, or even named until centuries after the ink dried. The parchment is cracked, the handwriting slants, the diagrams are colored by hand, and yet inside those diagrams are the compound crank, the camshaft, the feedback loop, the programmable drum, the pressure valve, the rocket, the diving suit, and the logic of every piston engine on Earth. 5 of these books survive. Each one predates the invention it describes by a margin that should not be possible. We are going to open all 5, and we are going to count them down in reverse, because the oldest and the strangest comes last. Number 5. Siena, northern Italy. The year is 1433. A city engineer named Mariano di Jacopo, better known by his nickname Taccola, is finishing a manuscript he has been working on for 14 years. He calls it De Ingeneis, on engines. 4 books bound together, hundreds of folios, thousands of drawings. The manuscript is timed for a royal visit. King Sigismund of Luxembourg is passing through Siena on his way to be crowned Holy Roman Emperor in Rome, and Taccola wants to present the book to him personally. What Sigismund holds in his hands that day is the single most important technical document of the 15th century, and nobody in that room fully understands it. Because buried in the pages of De Ingeneis are 2 mechanisms that will quietly reshape the next 500 years of human civilization. The first is the chain transmission, the direct ancestor of the bicycle chain, the motorcycle chain, the roller chain that drives every industrial conveyor on the planet. The second, and this is where the impossibility begins, is the crank with connecting rod, the compound crank. Stop for a moment and consider what that mechanism actually does. It takes a wheel going round and round, and it converts that circular motion into a piston going back and forth. That is the defining component of the steam engine. It is the defining component of the internal combustion engine. It is the defining component of the sewing machine, the locomotive, the water pump, and the pneumatic drill. Every car engine on Earth runs on this principle. Taccola drew it 400 years before the Industrial Revolution would run on it. He drew it while he was supervising road repairs in a medieval Italian city-state. He drew it next to sketches of harbor cranes and aqueducts and siege engines, as if it were just another useful machine. Taccola was nicknamed the Sienese Archimedes. He was a notary, a sculptor, a superintendent of roads, and a hydraulic engineer. His drawings influenced Francesco di Giorgio, the next great Sienese engineer. And through Francesco di Giorgio, they reached the hands of a young Tuscan polymath named Leonardo da Vinci. Leonardo's Codex Atlanticus, the most famous engineering notebook in Western history, contains chain transmissions and crank mechanisms that are demonstrably traceable back to Taccola. The man credited with inventing the modern machine simply copied them from the man who actually did. Skeptics argue Taccola only documented existing craft knowledge rather than inventing anything himself. It does not matter. The manuscript is the earliest explicit written record. Before De Ingeneis, the compound crank with connecting rod does not exist on paper in European civilization. After De Ingeneis, it exists in Leonardo's notebooks, then in German mining manuals, then in steam engine patents, then in every mechanical dictionary from the Enlightenment forward. There is a single doorway, and the doorway is a Sienese civil engineer sketching by candlelight in 1433, waiting for a king. Number 4. A man walks underwater in a sealed suit. Another sketches rockets arcing across the sky. Both drawings sit on facing pages of the same book, almost 4 centuries before either weapon reaches a European battlefield. Eichstätt, Bavaria. The year is 1405. A physician and military engineer named Konrad Kyeser is living in political exile. He used to serve King Wenceslaus IV of Bohemia at the court in Prague, until Wenceslaus was deposed in 1400 and Kyeser had to flee. He has spent the last 3 years in a small Bavarian town, writing and illustrating a manuscript he calls Bellifortis, Latin for strong in war. The finished book is roughly 140 folios of parchment, every page illustrated in color, every mechanism labeled. It survives today at the University of Göttingen Library under the shelf mark Codex Ms. Philos, 63. Kyeser dedicates it to Rupert, the new German king. What he presents is the first fully illustrated manual of military technology in European history, and it contains technology that European armies will not actually field for centuries. Turn to one folio and you find a man walking underwater in a sealed suit, a diving suit. Not a bell, not a barrel, a suit. The first operational atmospheric diving suits that actually work, the ones built by Karl Heinrich Klingert and later refined by Augustus Sieber, do not appear until the 1790s. Kyeser draws one in 1405, almost 400 years early. Turn another folio and you find rockets, recognizable rockets. Tube bodies, stabilizing fins, propellant charges, trajectories arcing across the parchment. European rocketry does not appear in serious battlefield use until Sir William Congreve's rocket of 1804, which terrorizes Napoleonic armies and earns a line in the American national anthem. Kyeser sketches the ancestor of that weapon 400 years before Congreve lights the first fuse. Turn again and you find handheld firearms, pole-mounted tube guns for infantry. Functional handheld firearms for general infantry use will not become standard in European warfare until the matchlock arquebus of the mid-15th century, and real widespread adoption takes another 100 years after that. Turn once more and Kyeser gives you the recipes. Saltpeter ratios, charcoal, sulfur, the precise proportions you need to mix gunpowder that actually burns. He also draws chariots armored with scythes, incendiary devices, portable bridges, scaling ladders, and a catalog of torture instruments. An exiled German engineer, sitting in a Bavarian town, hiding from political enemies, drew a man walking underwater, drew rockets arcing through the sky, drew soldiers firing handheld guns, and then wrote down how to mix the powder to make them work. None of these technologies would be standard in European warfare for at least a century, and some of them not for 4 centuries. Skeptics point out that Kyeser leaned on older sources. He cited Vegetius, Roger Bacon, and Arabic military treatises. True. But synthesizing diving, rocketry, and firearms into a single illustrated treatise, written in Latin, circulating through the courts of 15th century Germany and Bohemia, made the ideas portable. The manuscript is the distribution vector. Bellifortis is how the future weapons of Europe traveled through the present. Number 3. Picardy, northern France. The year is somewhere between 1225 and 1235. A traveling master builder named Villard de Honnecourt is filling a notebook. 33 sheets of parchment, roughly 250 drawings. It survives at the Bibliothèque Nationale de France under the shelf mark MSFR 19,093. We know almost nothing about Villard as a person. We know he traveled, and we know he sketched the cathedrals of Chartres and Reims and Lyon from the scaffolds. We know he was interested in geometry, in anatomy, in proportion, and in machines. And we know that when his notebook was rediscovered in the 19th century, it rewrote what historians believed medieval engineering was capable of. Turn the pages, and you find a perpetual motion machine. A wheel with mercury-filled hammers attached to its rim, designed so that the falling hammers on one side will always outweigh the rising hammers on the other, so that the wheel will turn forever without any input. It will not work. The physics does not permit it. But Villard is the first European and one of the earliest writers anywhere on Earth to attempt perpetual motion on paper. The concept itself, the very idea of a machine that runs forever, would not be named in Western science for decades after his death. Turn another page. A water-driven sawmill, not a simple water-powered blade, a sawmill with automatic log feed. The water wheel's axle drives a ratchet wheel. The ratchet wheel advances the log into the blade by precise increments. A separate mechanism engages a triangular frame to push the saw downward into the cut. A bent sapling pole acts as a spring, resetting the blade between strokes. A 13th century mason drew a machine that feeds itself logs, cuts them, and resets itself, all powered by the current of a river. This is a self-feeding concept rendered on parchment. Modern engineers have examined the drawing and argued about whether it would actually run. The argument is itself the evidence. We are not debating whether a medieval craftsman could imagine a self-feeding industrial saw. We are debating whether his specific drawing would function. Turn again, and you find the trebuchet, not a simple torsion catapult, a counterweight trebuchet with a trestle frame and a counterweight box, estimated at roughly 18 cubic meters, capable of holding 30 tons of ballast. Modern reconstructions calculate that this machine could hurl a 100-kilogram stone more than 400 meters. Turn once more, and you reach the drawing that for much of the 20th century was cited as the first mechanical escapement in Western history. Villard labels it with the line about how to make an angel keep pointing his finger at the sun. For decades, historians pointed to that sketch and said that Villard had drawn the heart of the clock, the component that regulates the ticking, roughly 60 years before the verified mechanical clock appears in European records. Scholarly consensus has since shifted. The angel drawing is not a true escapement in the strict horological sense. The debate is unresolved. But even without the escapement, the rest of the notebook is already impossible. A traveling Picard mason with no formal engineering education filled a notebook in the 1220s with a self-feeding sawmill, a perpetual motion wheel, a counterweight trebuchet capable of launching cars, a spring-wound crossbow loader, and grid-based proportional drafting of animals and human bodies. Villard was not supposed to exist. Not in the century we are taught was mud, plague, and superstition. Skeptics say he copied from Byzantine and Arab sources he encountered on his travels. Fine. His notebook is still the earliest surviving Western document that draws these machines with working detail. The portfolio is the leak. The knowledge was somewhere. Villard is the man who wrote it down. Number 2. A boat drifts across a palace lake. 4 robot drummers sit on it, playing a rhythm that can be reprogrammed by moving pegs on a drum. The year is 1206. The region called Al-Jazari, Upper Mesopotamia, in what is now southern Turkey. An elderly engineer named Badi al-Zaman Abu al-Iz ibn al-Razaz al-Jazari is finishing a manuscript in the final months of his life. He has served 3 successive Artukid sultans as chief court engineer. He presents the finished book to his current sultan, Nasir al-Din Mahmud. Its title in Arabic translates as The Book of Knowledge of Ingenious Mechanical Devices. Inside, Al-Jazari catalogs more than 50 machines across 6 categories: water clocks, trick-drinking vessels, phlebotomy devices, fountains and musical automata, water-raising machines, and miscellaneous ingenious devices. The finest surviving illuminated copy is in the Topkapi Palace Library in Istanbul. The manuscript does not merely describe machines. It introduces mechanisms that will not enter the European written record for another 200 to 500 years. Al-Jazari is credited with the first documented camshaft, a rotating shaft with cams attached, converting circular motion into precisely timed linear strokes. He uses it in water clocks, and candle clocks, and water-raising machines. The cam and camshaft will not appear in European mechanisms until the 14th century. He's also credited with the first known crankshaft combined with a connecting rod. In 1206, Al-Jazari draws a twin-cylinder water pump powered by a wheel whose rotation drives crank pins into linear motion. Functionally, it is identical to the crankshaft in a modern internal combustion engine. And then there is the boat. 4 humanoid figures sit on a small vessel that drifts on an artificial lake during royal banquets. The figures play drums, cymbals, and flutes. The rhythm shifts, the beat changes. The melody moves from one pattern to another. Inside the boat, hidden from the guests, there is a rotating drum studded with pegs. The pegs strike levers. The levers activate the musicians. And here is the detail that changes everything. Move the pegs, and the music changes. The machine is programmable. In 1206, 820 years ago, Al-Jazari drew the first recorded designs of a programmable humanoid automaton. The underlying logic, pegs on a rotating cylinder, triggering actions in sequence, is the same logic of the music box, the same logic of the player piano roll, the same logic of the jacquard loom, and the same logic of the Hollerith punch card that would eventually give rise to the computer. The binary architecture of programmable machinery begins on a boat floating on a palace lake in medieval Mesopotamia. Al-Jazari also designs the elephant clock, an 11-foot water clock housed inside a carved wooden elephant. Every half hour, an automaton strikes a cymbal, a mechanical bird chirps, a serpent pivots, a scribe's pen rotates to point at the time. It is the first clock anywhere on Earth in which an automaton reacts at timed intervals. He designs the castle clock, an 11-foot astronomical display tracking solar and lunar positions, zodiac signs, and programmable chimes. Historians of computing call it the earliest programmable analog computer. He designs the first double-action suction pump with valves, a key step on the road to the vacuum pump, and ultimately the steam engine. A dying Muslim engineer in a small medieval court in what is today southern Turkey finished a book and presented it to his sultan in 1206. Inside the book, he drew a boat with 4 robot drummers whose beat could be reprogrammed by moving pegs on a drum. That is the architecture of every computer now running on Earth, drawn 820 years ago. Number 1, a thermostat, drawn in Baghdad, 1100 years before the word existed. The House of Wisdom. The year is approximately 850 Common Era. 3 brothers are finishing a book, Abu Ja'far Muhammad, Abu al-Qasim Ahmad, and al-Hassan. They are the sons of Mūsā ibn Shakir, a former bandit who reformed and became court astronomer under the Caliph al-Ma'mun. After their father's death, the boys were raised as wards of the Caliph himself and educated at the Bait al-Hikmah, the House of Wisdom, the greatest research institution of the 9th century. They grow up to become the leading scientists of the Islamic Golden Age. And around the year 850, the 3 brothers complete the Kitab al-Hayal, the Book of Ingenious Devices. Inside it, they describe roughly 100 mechanical devices. This is the oldest manuscript on our list, and for the title of this video, it is the single strongest case. The Banu Musa manuscript describes machines whose underlying logic would not be formalized as an engineering discipline until Norbert Wiener's Cybernetics in 1948. An essay from the scholarly series Muslim Heritage states it plainly. The closest modern parallel to the work of the Banu Musa brothers lies in control engineering and pneumatic instrumentation, not medieval craft, not clockwork, control engineering. The field that runs every autopilot, every thermostat, every cruise control, every industrial regulator, and every process loop in every factory on Earth. The brothers describe the first known use of conical valves as automatic inline flow controllers. That is the working principle of every modern pneumatic and hydraulic regulator. They describe the first feedback controller, a device in which the output of a system is used to automatically regulate its own input. That is the architecture of a thermostat. That is the architecture of an autopilot. That is the architecture of cruise control. The Banu Musa built one in Baghdad, 1100 years before the word cybernetics existed. They described the first fail-safe logic. Trick vessels that permit small withdrawals of liquid but lock out after a large withdrawal. A deliberately engineered mechanical if-then statement. A logical gate built from copper, brass, and water pressure. They describe the earliest known mechanical musical instrument on Earth, a hydro-powered organ that plays interchangeable cylinders. Swap the cylinder, swap the melody. A programmable machine 3.5 centuries before Al-Jazari and 1,000 years before the first player piano. They describe a self-trimming lamp whose wick advances automatically as it burns. They describe gas masks specifically designed for workers entering polluted wells and mine shafts. They describe a clamshell grab, a dredging device lowered on ropes to scoop mud from the bottom of rivers and canals, operated entirely from the surface. That exact design, the clamshell grab, is still in use today on 21st century construction sites. A medieval Baghdad invention is still moving Earth on modern riverbeds. Skeptics note that the Banu Musa borrowed from Hero of Alexandria and Philo of Byzantium. That is true, and it is the wrong objection. Hero's devices are tricks, temple doors that open when a fire is lit, coin-operated holy water vendors, party pieces. What the Banu Musa added was automatic control, machines that sense a state, compare it to a target, and change their own behavior accordingly. That closed feedback loop is absent from Hero. It is absent from Philo. It is absent from every earlier source we have. And it is the single invention that separates a toy from a thermostat. It separates a music box from a computer. It separates ornament from engineering. In 850 of the Common Era, while much of Europe could not reliably light a candle after sunset, 3 brothers at the Baghdad House of Wisdom wrote a book. In it, a lamp that feeds its own wick, a vessel that drinks from a barrel and stops on its own when it has had enough, a music player with interchangeable programs, and a thermostat, 1100 years before the word thermostat existed. The discipline that studies machines like these would not be named until after the Second World War. The machines were already drawn before the Vikings reached North America, 5 manuscripts, 5 engineers, 600 years of calendar between the oldest and the youngest, 3 civilizations, 1 Italian civic engineer, 1 exiled German military physician, 1 traveling French mason, 1 Artukid court polymath, and 3 brothers at the House of Wisdom in Abbasid Baghdad. Between them, they drew the compound crank, the connecting rod, the chain transmission, the camshaft, the crankshaft, the programmable automaton, the feedback controller, the fail-safe logic gate, the conical flow valve, the self-trimming lamp, the hydro-powered programmable organ, the dredging clamshell, the gas mask, the diving suit, the rocket, the handheld firearm, the counterweight trebuchet, the self-feeding sawmill, and the perpetual motion wheel. Every one of these mechanisms appears in the historical record centuries before it is supposed to exist. Every one of them survives on parchment because somebody cared enough to draw it carefully, label it clearly, and protect the manuscript for 800 years or more. Think about what that actually means. Somebody in Baghdad in 850 drew a thermostat. Somebody in Mesopotamia in 1206 drew a programmable robot. Somebody in Picardy in 1230 drew a machine designed to feed itself logs and cut them without a human hand. Somebody in Bavaria in 1405 drew a man walking underwater with a sealed helmet while also drawing rockets and handheld guns on facing pages. And somebody in Siena in 1433 drew the single mechanical conversion that every piston engine on Earth would eventually depend on. None of these men had electricity. None of them had steam. None of them had the metallurgy, the precision tooling, or the industrial supply chain that the 20th century treats as the price of admission for serious engineering. What they had was paper, ink, geometry, and the stubborn refusal to treat the future as somebody else's problem. The textbooks will tell you the Industrial Revolution was a European phenomenon of the 18th century. The manuscripts tell you something else. The manuscripts tell you the Industrial Revolution was a library. It was a slow, patient, manuscript by manuscript accumulation of mechanisms drawn by engineers in Baghdad, in Diyarbakir, in Picardy, in Bavaria, and in Siena across 6 centuries, in 3 civilizations, in 4 languages, on cracked parchment that somehow survived fire, flood, plague, and politics to reach us. The modern world did not invent itself. It inherited itself, page by page, diagram by diagram, from engineers whose names most of us were never taught. The blueprints were already drawn. We were just the civilization that finally got around to building them.